Ladies and gentlemen, distinguished guests, chairman, colleagues, I am delighted to welcome you all to the university this evening to celebrate the work of one of our most accomplished academics, Professor Wilfred Otten, who holds the chair in biophysics of soil ecosystems here at Abertay, as well as being co-director of the Scottish Informatics, Mathematics, Biology and Statistics Symbios Centre based at the University of Abertay, Dundee. This evening I'm joined by my colleagues, the Acting Vice Principal and Deputy Vice Chancellor, Professor Steve Olivier, on my far right. On Professor Otten's left is his head of school, the head of contemporary sciences here at the university, Dr. Nia White. I would also like to extend a welcome to members of Professor Otten's family who are with us this evening, to his parents, his sister, wife and 3 daughters. You're all most welcome to the university. Professor Otten's accomplishments are truly of international significance, and the university is extremely proud to have him as a member of its staff. His global reputation as a soil scientist reflects Abertay's standing as a university and its continuing ambition to hold leading positions in both research as well as teaching and learning. At the heart of any university is research excellence, and our Scottish Government can be justly proud of Abertay's achievements here. And I can think of no better exemplar of that than Professor Wilfred Otten. So from where did such a remarkable and excellent scholar emerge? Wilfred trained as a soil scientist in the Netherlands at the Agricultural University Wageningen, with apologies to the Dutch speakers in the audience, completing his PhD in 1994. After a brief spell as a computer programmer, for which we excuse him, Wilfred embarked upon an academic career beginning in the Netherlands and more recently here in the UK. Professor Otten worked at the universities of Oxford and Cambridge before joining Abertay some 5 years ago. And during those 5 years, Professor Otten has made a significant impact on the research profile and operations of Symbios and has contributed greatly to the life of the university more generally, acting as a mentor both to students and colleagues. And on a personal note, I would like to thank him for the many interesting interactions that we've had, me as a senior manager of the university and Professor Otten as one of our leading academics. Those of you in the audience who are aware of these sorts of discussions can, I'm sure, imagine the very interesting exchanges that we have had over those 5 years. As a researcher, Professor Otten has set a blistering pace with 40 refereed articles so far in his career and many, many other articles and conference presentations. He is co-chair of the Journal of Hydrology and co-chair of the British Soil Water Physics Group. Therefore, this evening, it is right to be able to claim we're about to hear from a world expert, and I now invite Professor Otten to deliver his inaugural lecture, Soil Research Matters, Only a Thin Layer Stands Between Humanity and Extinction. Wilfred.
Ladies and gentlemen, thank you for coming to my presentation. Professor Terry, thank you for your very kind introduction. And I'm very pleased to be able to give this presentation, and I hope you will enjoy it. As title I gave, Soil Research Matters, Only a Thin Layer Stands Between Humanity and Extinction. And since I decided to give it that title, there have been numerous people coming to me and wanted me to ask, how long have we got? Now, I'm not sure I'm going to give you that answer because you may not like it, but I'll give you some hints about the threats that we're facing and what's going to happen if we don't live up to those. We'll have 2 parts to this presentation. The first part is I'm going to look at sustainable life at soil. And that's really looking a bit at our history. So what's happened in the past? Because what's happened in the past is going to tell us what's going to happen in the future. The second part of the story will deal with sustainable life in earth or in soil. And the reason for that is because those 2 are coupled. And below that, I want to make a statement to start up with for us to realize that many years ago, about 98% of people would work on the land and would live from the land, and they would understand the land. These days, about 1% of people is working on the land and is supporting the rest of us. Now that tells us what could be wrong with society, because the decisions what's going to be done with that land is being made by other people, no longer by the people that actually work on the land. And that puts an awful lot of responsibility in those people in getting it right, because the knowledge is with very few. So unlike oil, soil is not considered of strategic relevance. And I hope that at the end of this presentation you realize that that should be the case. Those who forget the past are condemned to repeat it. That is a very famous statement. Most of you will have heard it. So what we'll do first is we're going to look at what history tells us about our dependence of soil. So what can we learn from that, and what is ahead of us? So one of the civilizations we take out first is the Mayan Empire. So when we look back 250 years AD to about 850 years AD, and it was a very strong and well-known civilization. So it was in the area around Mexico, Honduras, El Salvador. It's not totally known what its origin was, because it actually emerged from several different societies that were interacting with each other, and at some point formed what is known as the Maya culture. Now, it was characterized by actually rather large cities for those days, about 10,000 people per town. So it's a pretty well developed culture and civilization. They were very advanced, so complex step temples. They worked and developed a lot in mathematics. They invented the concept of zero. Now, that may not sound very ambitious these days in the era when we invented billionaires and going in debt. But of course, if they hadn't invented zero, we couldn't go in debt. So they had the 365-day calendar, and they have accurate maps of moons and planets. And that is really an advanced way in those days. So a very advanced culture and a very advanced civilization. And their agriculture was really what was driving it. So they had really advanced ideas. They had permanent raised fields, and those ideas are still sometimes occurring in some of our present agricultural systems. Terracing, forest garden, but they also had a slash and burn culture. So they used the land, burned it, and moved on. They lived from local produce, something which we advocate these days a lot, and that was already done in those days as well. So their agriculture was really advanced for those days, and that really was what was driving their civilization, which really made them as strong as they were. They knew they were dependent on water. Water was a problem, and they created massive reservoirs to store the water that they were needing. So society was thriving. The rich got richer and got fatter, and the poor got poorer, and degradation set in. So that's where the first sort of sounds begin to come up. That sounds familiar. So there's no silver bullet. There's no real single point where we can say, well, this is what caused it, because we're dealing with drought, we're dealing with diseases, social decline, we're dealing with warfare, all sort of symptoms. But these are really symptoms, because what was underlying it is that they were running out of food and running out of water. For centuries, they paved their best land. They stripped the hills, they used it for timber to build their water reservoirs. They were not thinking ahead. So they had the problem, they were able to resolve it, they were very advanced, but as a result, they eroded their soils at a phenomenal rate. So the origin of their existence and their thrive was in the end what put them down. So the ultimate reason for their downfall is that they've been unable to cope with the environmental change. They built a system which was highly dependent on their agriculture. When the climate changed a little bit, the society collapsed. Another example, which is near a floodplain civilization in the area of Pakistan, the Harappan civilization, slightly different. They actually formed around a river basin, so a river plain area, and they managed to find a way to exploit that. So they made use of rivers flooding the area, fertilizing the land, and actually using that, and they managed to control that. They built big cities. They had a long spell of success in there. They had very advanced cities with a very regular layout, and over about 100 towns and villages were occupying the valley. So they were more living from merchandise, so they were trading with areas and societies around them, and again, they thrived very well. Irrigated culture was their main source of living, and that was what their society was built on. They had a huge range of crops: wheat, barley, peas, melons, sesame, so they were doing quite well. They collapsed, and for a long time they collapsed actually quite abruptly, and that was in first instance, it was actually blamed that people felt, well, they've been invaded. They were foreign invasion and they were forced out of their country. And that's been long the thought, but more recently people have looked into it and they've actually found some evidence that they were beginning to move out before the invasion was there. So society was collapsing. And again, the reason was there that they'd been abusing their soils. They were running out of fertile soils. They couldn't sustain. They were gradually moving out. Society was gradually collapsing. People were getting dissatisfied. They became generally weak and they became more susceptible for invasion. So they called that more or less upon themselves. Numerous examples like this we can give. If we look at the Greek civilization, characterized by deforestation and soil decline, they needed a lot of wood for their bronze statues, and they just harvested everything around the area. They heavily grazed it subsequently and didn't allow for any regrowth, and that became their downfall, or contributed to their downfall. The Roman Empire, again another example where they failed to manage their resources. They degraded their own land, they needed more wood, they couldn't provide the wood, they degraded it even further, then they needed even more wood for their ships to get war with other countries, and ultimately this was no longer sustainable. Iraq, not of course a civilization that's completely disappeared and it thrives for other things we know, but I put it down here because very few people actually realize that that's an area where agriculture started a long time ago. And when we look at the area now, it's hard to believe that that is one of the most fertile areas in the past when we look at it now. So that's what's happened to our soils. So why does everything so depend on soils? And what are the key challenges that are facing society today that are really so much dependent on soils? Well, food, that's an obvious one, and it's always been at the forefront of soil scientists. We've always focused on that. But there's other ones, energy, because we're getting more competition now for biofuel crops, pollution and recycling. Really, soil is a sort of a big sieve, and it's got a massive contribution to make to recycling and to cleaning our water. Water, the next one in the list, is really going to be a big problem for us to sustain. It's not just the soils. Climate change, and I'll elaborate on these sort of things a little bit more about the role that soils has in climate change, and ultimately nutrients and minerals. It is not very much in the news, but we're going to run out of phosphate. And phosphate is one of our key fertilizers that our agriculture is based upon. So we think about oil, we think about soils, we think about food, we think about water. Phosphate is the quiet one. So if we look at feeding the world, and I put that up front because really when we think about soil science, agriculture has been our main sort of thing for most soil scientists. That's what we focused upon, basically because it's what society asked from soil scientists. Find a way to grow our crops. Now, world population is going to increase. We all will have heard that. What people know less is that that increase is mainly going to happen in developing countries. So there's a huge disbalance about where we're going to find that decrease. And that poses extra challenges. Now, the expectation is that by 2050, we live at about less than 0.1 hectare per person. Now, that's less than half of what we're achieving at the moment. And we may think that we will improve our productivity, and no doubt we will. But even that might be a challenge, which is too much for us to imagine. And then we just talk about sustaining our current levels, not even about coping with a growing population. So what is the challenges that we do face here in the food? What can we still do? Well, there's two sort of policies there, or two sort of objectives. In the developing countries, we really need to decrease the gap between the yield and what is potentially possible. And in the developed world, we've got another problem because actually we've already quite well achieved what our potential yield is. So there the challenge is to find ways to increase the sort of soils that we can using and expand our ways in areas. So there's different sort of challenges that we're facing depending on which side of the world we look at. But this is the sort of butter stuff that soil scientists have always dealt with. So this is not an impossible challenge. The ultimate goal we need to achieve will be a challenge, but the questions are the ones we are familiar with. The problem we might face is that our long-term losses may show up as short-term economic gains, and that is one of the challenges that we shall need to keep an eye on. So finding more soil, I just put a map up here, because when we think of soil, you might think, well, there's enough around. Well, this is a bit of a map of where we are and where the problem areas are. And actually, there's a problem virtually with every soil. But if we take out the big ones, the yellow bit is where we've got problems with irrigation and water and drought. And more in the north, we really have constraints which are more related to temperature, so there's a huge area of soils that we can't use. Then we've got big areas in the right, in the purple area, where our slopes are too steep. We've got areas where the soils are too salty, where they are too polluted. So we're facing a huge variety of challenges that we have to deal with and have to resolve. So finding extra soil is not as easy as it may look. So we may look around us and we may think, well, there's enough around, why don't we exploit the other areas? But it isn't always possible, and we'll have to find solutions, and we may have to clean up some areas first. The other thing you should point out at the map, why are we focusing on soil? Just look around, most of it is water. So why are we not concentrating more on water? And perhaps we should think about that the next green revolution should really be a blue revolution. Water, there's a lot of water around, and you showed it on the map. Unfortunately, we can't use it. There's only a very small percentage of water that we can use for growing our crops. The rest is salty, so we can't deal with it, we can't use it in the land. But soils play an enormous role in provision of water, and we don't always realize that. So most of the water that we can use actually circulates through soil. And there's two things we have to think about. I don't think people realize how much water you actually use. For every cup of coffee, 140 liters of water has been used to make that cup of coffee. So that is something you really have to think about. You know? A slice of bread, 40 liters. A steak dinner, well, think twice. You know? If we run out of water, we may have to have a better understanding about how much water was actually used to prepare our food and make some decisions based on that to reduce our shortage of water. So for soil scientists in particularly, we focus on can we make use more of what we call green water. Now that's not really referring to the color, it's more referring to the water that's actually stored in soil rather than the water that comes from rain. So if we make more use of that, then we can find better ways and our dependency of the water coming from the rain becomes less. Now that is a typical soils question. We can deal with that. We can focus our understanding of water movement through the soil environment related to that. But in addition to that, we'll have to get a better understanding for different crop types and where they grow, how much water they use. And we may need to start thinking about putting the crops that use a lot of water into areas where we have better access to green water to get that balance right. So we may need to start thinking about different decisions and not just focusing on the production, but also focusing on actually the water use. Soil and energy. So we have bioenergy or biofuel crops coming up. It is a big area of discussion. I have to admit that this picture here is taken from a group that's against biofuels. So this is you can either say a more optimistic or a pessimistic view, but it is one of the scenarios which people look at. And whatever way we look at it, if we look in the future, you can see that there's an anticipated increase of areal that's going to be used for crops. But the major increase most likely is going to be in bioenergy crops. And it's not just a decision between crops for food. It is actually, it's going to be taken out of our forests. And we can say, well, okay, who cares about the forests? But those forests, if we're going to take them and going to put them more into bioenergy crops, we'll have to start thinking about what's going to happen with the carbon in the soil and what are we going to do to our climate. So it's that overall systems approach and system understanding we need to have. And for bioenergy crops, we know very little. We know very little about how it affects the water use. We know very little about what it does for the biodiversity. And we don't very little know about the positive things, like if we get biochar, how is that going to use to improve our lands? So there's positives and negatives there, but for all of them, we've got a very little understanding. And there's much work for us to be done. Now last I put down here is soils and our climate, and that is something which not everybody is aware of either, but a phenomenal amount of carbon is stored in our soils. And the balances are very, very tight in there. So currently at the moment, soils have absorbed carbon into the soil, and that's been the most dominant process. But there are early indications and some studies in the UK where there are indications that our soils are beginning to lose some carbon. Now, if that's going to happen, if we're going to tip that balance from absorbing carbon to releasing carbon in the atmosphere, then we're going to accelerate our climate. And we may end up with a scenario that our climate is going to run away and the developments could be catastrophic. Now, that's a doom scenario which we don't want to believe in, but there are positive things to think about here, because if soils have always absorbed that carbon, can we put our knowledge to finding ways to get it to absorb more carbon? So that's where our research can focus on. Again, there's limits to what we can do there. We can enhance the carbon storage. It's not going to resolve our climate problems. We'll have to do other things for that. But what it may do, it may buy us time. And time can be a very crucial factor in how we're going to cope with all those challenges. So these are the examples and the challenges that we're facing. And as Roosevelt pointed out, a nation that destroys its soils destroys itself. So we are aware of this. So we've seen the examples from the past. We know the challenges that we are facing. We know the role that soils plays in it. Now, if we have all that knowledge, surely we're getting it right. There's no way that we can get this wrong. Well, maybe there is. So this is an example from Phoenix 2011. If you wonder what that cloud is there, it looked like a scene from the Mummy movie. It's soil. So this is where our soils is. And this is not a rare event, although we prefer to call it a freak weather event. But actually, it's a poor soil management event. And it's a combination between those two. But these events are occurring more and more. And actually, about 100 years ago, this is where we had those problems in the US, which started off the forming of the Society for Soil Science in the US. Because at some point, the people on the east could taste the soil in the west, and there was a massive dust cloud hanging over the US. And people began to die from dust inhalation. And at that point, the government realized we're doing something wrong. They called up on the scientists together, and they resolved the problem. So we can deal with those problems. We can resolve the problems. But we haven't got it right everywhere yet. And this is increasing. So this is in the US. They're not alone. China, that is a picture I took myself, so I actually can confirm that this is really happening. And it is most inconvenient when your plane gets grounded because the soil from the north is blowing down into your airport. And this can be massive. So it can be so massive that it can be seen from space. So here we've got an example, and when you look in that curve, you wonder what it is, that's soil. So that's where our soil is going. And we don't realize this. We think it's safely, and we think we're standing on it, and it thinks it stays down there. But this is where it goes. And this is just examples of wind erosion. We're not talking yet about water erosion, and that is phenomenal too. It's clogging up our harbors, so we've got immediate economic impact of the soil erosion. And that actually doesn't even make us think yet about what's happening with the soil that's disappearing and upon which our society is depending. So 99% of the world's food comes from soil, but each year we're losing 10 million hectares. So we think about we need to produce more soil or more food, But we don't think about it. Actually, we're losing at the same time our soils. We just think we can resolve this. And we really have to get our act together. So some ideas, 300 million hectares has already been gone. So that's an area large enough to feed Europe. And Iraq, that area, has been one of the examples of it. So it gives you a bit of an idea about the challenges that we have faced and what we've done to our soils so far. So don't get the false impression when you're here in Scotland and you look around you and see all the nice green hills that we're okay. This is not something that happens elsewhere, that they can't manage their soils. Actually, it happens everywhere. It just isn't very visible in every place where it happens. So 40% of our arable land has already been degraded. Now that is a phenomenal amount. And if we think about doubling our food production, that is an area where we could have focused our attention on. We should have done it many years ago. Now maybe we can restore it, but we certainly should make sure that we're not going to lose more of this. So again, in a similar way as how much water we're getting for food, we can think about how much soil is actually lost per kilogram of food, and you can see there's big differences there between different areas where this comes from. Again, in the same way as that we've got some food labeling, maybe we should start thinking about getting a better realization for people about what it costs to produce food. What is the damage we're creating to our environment? I put up Biosphere 2. That's probably one of the biggest ecological experiments and one of the biggest failures. Because in 1991, we thought we understand the environment. So we're going to build it. So we built a closed system in the US. We put 8 people, 9, there's 8 people in there. They were called Biospherians. We had plants in there, we had insects in there. We thought we can live in this closed system. We fully understood it. Well, we were wrong. So we didn't survive. Of all the insects and insect species, only 6 survived. So that were the first symptoms. They were the first to go. Oxygen levels were dropping. CO2 levels were rising. It's all got a familiar ring to it. And they had to take action to survive. Now, what did they get wrong? Well, there were a few things that go wrong. But one thing that they got wrong is that they thought we've got to make sure that our crops and our plants in that building are going to grow. So they gave it a lot of organic soil. And that lot of organic soil, they forgot that there's bacteria in there and that they produce a lot of CO2. So there were unexpected events in there. Then a second unexpected event was the interaction with the pavement. So there was some chemistry going on in there. And these things weren't thought through. So we had some aspects of our understanding of the environment that was lacking. There hasn't been a new attempt since. The facilities still exist, but we began to realize that we can't run it as a closed system. So it's an open system now where we continuously are putting our fresh air in there. Now, it's just an indication that we do not understand our environment. We think we've got that understanding, but we don't. So what's required? Well, really, to get our understanding, and that last example gave already an idea what's going on. We really have to start looking more at our soil and really look inside our soil. What's happening inside that soil? What is the missing bit of our understanding? So now I've got a schematic diagram where we all make it. So we've got some sand grains, we've got some finer clay particles, organic matter in there, and a lot of pores in there. So soil has got a lot of airspace in there. Larger pore volumes, about 35 to 55% for arable soils. There are more extreme examples, but it gives you a bit of an idea. And those pores have got a phenomenal range in sizes. They can go from nanometers up to centimeters. So what does soil offer? It offers adequate food supply, it offers water, it offers oxygen, it offers a shelter, refuge from predators, and it offers a space with which organisms can interact. So really, in that little environment, it provides everything that life needs. And it provides it, and it provides it, and it delivers it in a spatial organization that everybody can access it. And that's quite a remarkable system when we think about that. So when we look at that, so soil is full of life. And let's not underestimate this. A little handful of soil has got more organisms and bacteria in there than we've got people on the planet. So we're not alone. And we are competing. We're competing for sustainable life. This is not a friendly neighbor. They can help us, but it's not necessarily their task. So soil is full of life. If we put some effort in there, we can investigate it. And we've all smelled it. So after rainfall, we probably experience, in most cases, a bit of a pleasant smell. At least most people think it's pleasant. And that comes from microorganisms. People have even tried to, that's time to get up in the morning. People have even tried to make some nice and bottle it and try and sell this. So that's. So how is that life organized? Well, when we think about those phenomenal numbers, it will give us the false impression that life is everywhere in soil. And that's the first mistake that we can make. It's not everywhere. It's spatially very heterogeneous. So what you see here is a slide which was made by a colleague in France. And that shows the spatial distribution of bacteria, here shown in blue, within the soil structure. And this comes from an area in topsoil where the density is very high. So this is about as dense as it gets, the population. If you go down deeper in the soil, you very often might be lucky if you find a few bacteria. An example here of some fungal hyphae that were growing through soil, again at very high density, so you see some soil particles and pores in between, and quite nice pictures, quite colorful pictures of fungal hyphae exploring this environment. So we've got some techniques in place that we can understand how soil environment is and what it does and how it interacts with life. An example of root growth here, and root is not just something which will follow our soil structure. As you can see, it almost curls up to put a force on there and put the soil out of the way and plow his way through the soil. So soil structure, as you could already see from those images, regulates many of the processes in soil. Now, despite that, and despite the fact that we know it, most soil science is still done by digging up a field, breaking up the structure, and quantifying it. And that comes from that concept idea that if we take a lot and we mix it, we can study the average behavior of it. And that is wrong. So we study factors of stability, but we actually are no longer looking at the structure which is making it function. And I always say, it's like looking at a building. When you want to buy a house, it's not being sold to you as the materials it's being made of. It's actually being sold to you how many rooms there are, and you look at the layout. Now, that's the way we should look at soil as well, the functioning. What you definitely don't do is you blow it up and pick up a piece of rock and say, well, this comes from the living room, because you'll be unable to have a look at that. So we've got a great insight in the stability of soil, but we've got very little insight about the rooms that makes it function. So what do we do at Symbios, at Abertay, here about that? We've made that really a focus of our study. So we really said, well, it's that's driving the processes and where we lack our understanding. This is what we need to zoom into. And for that, we either take our facilities upstairs, which are X-ray tomography systems, which enable us to look inside soil without breaking it up into little pieces. If we want to go a bit more advanced, we go to synchrotron facilities, which are there on the right. In both cases, we have moved away our science, and we take a little bit of soil and we put it in a big piece of equipment. That's the way science appears to be going. What do we see? You can see here, which is just a cylinder of soil. And you can see the solid phase in there, and you can see some pores, so it will run as a movie, and in a moment it will take you inside, and it will give us an idea about where the macropores are. So really, where are the living rooms in this soil environment? This is the environment in which all the processes take place. So this is where that water flows through, that's so important. This is where all those organisms interact with each other, and this is what defines how they interact with each other. Now we'll move on. If we look inside soil, we will see that it's hugely diverse. So if we take the sample from one area, it's going to be very different from another area. So what can we see in those gray images? I hope you can see it, and it's not too light here. But we see some areas of roots and solid phase, and we can see some pores. This is a top layer of a soil more from a forest area, and you can see it looks completely different: mineral particles, pores, and organic matter. Now we put some arrows in there as if it's very easy to do, but it's not an easy question to identify what it is. And actually a huge part of our research is to develop robust ways to make that criteria and decide what's in here. What does it look like? So we've got a little cube of soil here. The first thing we do is we identify what the pore spaces are, and they will appear at a moment, and now you can see on the outside of the cube where the pores are. So this is how it's going to interact with the environment. This is where all the water and oxygen will flow through. Now what we do in a moment, we're going to take away the solid phase in between, and then for most of you at least, for the first time, you'll be able to see what soil looks like on the inside. And it will gradually appear for you now. And here you will see the very complex geometry that we're dealing with. This will determine how organisms interact with each other, how water will flow. Soil management has got a huge impact on that. Same soil type, but has been used on a wheat rotation, no tillage or reduced tillage, or in native successions for many years. So you can see the way we manage our soil is affecting the way our structure looks like. Now that's not surprising, but both of them function for the purpose we had in mind. The question, of course, is how quick did that change? And if we're going to change our land management, which we'll have to do in the future, what's going to happen with those structures? Are they going to reverse back? Are they going to change back? So these are some of the questions we do. Now, it doesn't allow us to look at biology. For that, we still need to cut a thin section through the soil. So here you see some structure. Then on the bottom here, an example where I showed you before how we can look at a very small scale, how fungi will mow through the soil. On the right here, the black boxes are area where we could see it, and the white is area where we had no fungi after they were spreading through it. We can overlay it, and you can clearly see how the organisms are finding their way through the soil structure and how they interact with each other and interact with the structure. There are some questions, however. Why are they in these areas? So how do they get there? Because they don't seem to be connected with each other. And why are they not in the other areas, which look equally suitable to me, at least? So there are some puzzling effects which we don't get from those thin sections. There again, the connectivity of that space is really a 3D thing. So we have to put this into our 3D context, and that's what we're trying to do. So two examples here. We take two ways of looking, or two examples of where we had our fungal distribution within that structure. One is far more densely compact than the other one. And as you can see, it's a bit like a lazy organism, I always say. If there's a lot of space and there are highways in there, it just races through them and it bypasses the more denser areas of your soil. If we're going to look a bit more closer to that in 3D, then this is what that soil sample looks like on the inside. So this is the area where those fungi had to spread through. 80% of that pore is connected with each other. In the other sample, which was more densely packed, a lot of the pore space at the resolution we can look at is no longer connected. So this was the largest connected cluster we could find. That's the second largest one. And I won't go on, but we could actually look at how the distribution of those sizes is. What I will want to point out is that when you look at it in detail, you can see here that two organisms in the white space, the pore space, can be very close to each other, but they can't interact. To interact, they will have to move all the way and find their way through that pore space before they can interact with each other. So proximity is not a criteria, and that was the criteria that we could see in those 2D sections. It's actually the pathways that we need to study, and we can only get at those in 3D. This is just a little example. If we move through that pore space, and the gray areas on here are connected with each other, and the white bit are not. Now picture yourself, think yourself as an organism in the gray area, and if you pick a gray area and you move down through that soil sample, fairly quickly you have a dead end. Yet all that gray is connected with each other. Now this is a dark and a hostile place, and you'll have to find and navigate your way through that 3D system. It's quite a challenge, and it's quite remarkable how organisms are succeeding in that. But it gives us an idea about the challenges that organisms are facing, and it gives us an understanding about how that environment can be so diverse, how organisms can be separated from each other in an environment like that, why they're not outcompeting each other. So it gives us a bit of an understanding of the reasons for biodiversity. Now, what will happen if we're all going to do this and we're all going to look at this microscopic scale and we leave behind our bucket and spade science? Well, I'm sure we'll make major advances in our understanding, but we'll have a danger that pretty soon we've got a better understanding of life on a sand grain than that we understand our field. So we need to do something to bring that up to more realistic scales. Now, we haven't got the answer to that yet, but these are the challenges we are addressing. And I'll give some examples for that: biophysical modeling, experimental design, and nonlinearities and emergent behavior. Biophysical modeling is something our group is particularly strong in. This is some work done by Ruth Falconer. And really, this enables us to model fungal growth through that complex medium. So you can see here, we took away the soil for convenience, so the green areas in here is actually from left to right, how organisms are exploiting and exploring this environment, this complex environment. Now we can put two organisms in there, and this is where it already gets interesting and actually fairly simple. And I always say, if you put two organisms on a plane, they will always mate. If you put two organisms in a 3D environment, it depends on how complex that environment is. They either will always mate or they will go past each other. And this could be one very important criteria about species interactions and about understanding the mechanisms that contribute to the diversity in soil. We can't just rely on modeling. We'll have to think about representing this in experimental systems. This is just a little example that we are thinking of now, and we're using 3D printing technology. So this will give us an opportunity to have and take our soil and scan it, and we take that complex structure and we print it, we reproduce it, and that gives us a physical, very complicated structure in which we can study in a controlled way how organisms interact, as you can see on the top picture. So novel experimental systems, novel ideas. And this really will give us an idea to understand more about not just the diversity, but the adaptation and the evolution of organisms. Because make no mistake, that's a very diverse population we have in soil. They will adapt to the challenges that will be thrown at it. Humanity may fail, but the bacteria will find a way. Emergent behavior, I'll give a little example of that. And I wonder whether or not we can learn from epidemiology. Why? Well, it's a biological system and an ecological system. But it's a system in which we have learned to understand it. It's about dealing about invasion of organisms, persistence of organisms. These are questions that are highly relevant for soil biology. We do get it wrong sometimes, but that's not because we don't understand it. It's probably because we refuse to put the correct policies in place. I'm going to take an example here of fungal growth and percolation, so a theory from physics to bring a better understanding. And the way we look at the environment is say, well, it could be a discontinuity of patches. Now, those patches could be plants. That's a very clear example of discontinuous, regular patches. They could be roots. So bacteria could colonize the roots and find a way to interact with each other, and individual roots are spatially separated from each other. They could be those areas in soil that I mentioned to you before. We can think of many examples. In all of them, I would argue, it's convenient, in first instance, to visualize spread through a population of discrete sites on a lattice. So let's start with that one, and let's see what the behavior of that would be. Now, what very many people do not realize, that if we look at a regular lattice, and from that we are removing some sites, the white bits, which are no longer available, and we introduce an organism in the center of it. Now, if 42% has been removed, the organism will not invade the area. If 40% is removed, it will invade the area. So that really is a very tiny difference in our environment, which will make a tremendous impact and will have a difference between not invading or invading. These are almost tipping points in environmental systems. Now, physicists are aware of those tipping points. Environmental scientists and biologists are less aware of it. We tend to rely on our systems to buffer us against these sort of events. And we think that things are linear, and if we understand what's happening now, we can extrapolate. It's not going to be the case. You can say, okay, this is theory. I don't believe in theory. Some do, others don't. So we put some experimental data on that to test this. And it's not exactly the same, but that's because theory is for infinite systems and infinite timescales, and we don't have that much funding available. So we're a little bit restricted in there. And you would expect a smoothing of there. And for here, we're not looking at an exact match. We were looking at demonstrating the principle. So a little difference in our population and in the way our population will spread can have a tremendous impact on the way the system behaves. And that is the important message that we wanted to demonstrate with these sort of systems. So can we extrapolate that to soil? Well, that's what we try to think of now. So here we can see just a little example in 2D, how we derive from that a network. And we can think theoretically what sort of networks that are most representative. But of course, we've got the advantage here because we've got our 3D network. We scanned it and we quantified it and we determined it. So we can derive the real networks from that in 3D. So this is a simplified representation of that very complex structure. And here the different colors are representing the width of the pores. And when you look at this, I always say, well, this is a roadmap for soil. And we've got a metropolitan in the bright areas, and we've got the rural areas surrounding it. And if a road gets blocked, we know that we get problems and we get traffic jams. Soil is not different. So minor effects in soil can have a major impact on how the environment is going to work. I'll show some slides here in the end, which is work which is currently being done by Paco Perez-Rocher in our group. And that really is taking those ideas into 3D. And what is already demonstrated there is that those thresholds, which are shown for you in the simple 2D systems, also exist in our 3D system. So we have got the clear evidence here now that we can expect very nonlinear reactions in our soil systems, which means that tiny changes, and they can be introduced by organisms changing a bit, and that might be simply temperature. So temperature may just change organisms a little bit. And that means that a tiny change in our environment may not have an effect, but then if we change it a little bit more, we may just go past that threshold and we may change our system substantial. Now, those are dangers that we don't fully understand and that we really have to focus on. So these are some of the examples that I put forward to you. So where do we go from here, you say? Because actually, okay, we get a bit of that understanding, but what it's going to get us. So, well, really, the future soil scientist is clear. It will have to work in an interdisciplinary team. It goes way beyond the traditional physics, chemistry, biology. We have to think about societal interactions in that as well. So this is not a skill that a single person can have anymore. We need to work in interdisciplinary groups. But how do we approach it then? Well, unfortunately, we're scientists, so first we create a new buzzword. Now, we've been through a few: intensification, green revolution, sustainable agriculture, ecological farming, organic farming, and probably most of you will have noticed that it's getting a bit quiet on the organic farming area. We seem to have forgotten that fairly quickly. So sometimes they pop up, those buzzwords, and then they go to sleep again. So what is the current thinking, particularly in the UK, which is being pushed a lot here? And that's sustainable agricultural intensification. Now that's put forward by the Foresight report a few years ago. And it really focuses on producing more from the same area of land while reducing the negative impacts. Now you think, oh, we're great, we're happy with that. But if you read in between the lines, it basically says, we're going to do the same as we've done in the past. We're going to rely on technological advances to get us out of trouble. Now, this has been the UK vision, and it's been pushed because it's technology driven, and that's the area we like to move into. The FAO has taken another direction, and I think this is the direction which is now winning in the UK as well. And that is looking at it at climate-smart agriculture. Now, this means that we no longer put the food production at the front and as our only goal. We actually look at our climate system. We realize that soils play a role in that. Yes, we need to produce more food, but it's not the only thing we can do. We can develop resilient systems. We can reduce our greenhouse gas emissions. And we need to find a way of sharing the food and enhancing our food security. So we don't have that single focus on food production anymore, which the UK has been promoting, and really, which has got us into trouble. It will get us out of trouble for food, but it's going to give us more trouble than we would like to deal with. So it doesn't mean we know how we're going to do this, because we're going to face some challenges, and I really think we're looking at a bit of a balance, because on one way, we've got the soil scientists who really need that innovation in our understanding. So we need the novel science and the curiosity-driven science. But on the other side, we haven't got the time. So we need to find the rapid solutions to the questions that we imposed of us. Now, the innovative understanding, I think we need particularly focus on the interactions that are between the different areas. So we need to focus more on systems approaches and really start understanding the way things interact with each other. But getting this balance right is absolutely crucial. If we get it wrong, if we're going to focus on our rapid solutions, then it's going to tip in one way and there's only one outcome. If we're going to focus just on our innovation and our understanding, we're going to tip the other way and we're going to be too slow. So we need to get that balance right, and getting that balance right is the only way. So is climate-smart agriculture the way forward? Well, probably what we need is climate-smart planning, because it's not just the agriculture. We need to get rid of the agriculture and really start thinking, how are we going to plan for the future? We can no longer think that we are the most central point on this planet. We're part of an ecosystem. And like they say, environment is not something you visit in the weekend. You're actually part of it. So that brings me to the end of the presentation. I hope you've got some ideas about the problems we are facing. And I really would like to thank the university as an institution for giving me the opportunity to do this research. And it's not just the opportunity, but I think it's also for offering a very exciting environment. I pointed out we need that interdisciplinary research. And this university is offering that interdisciplinary nature. Now, interdisciplinarity is preached by many, but practiced by few. And it is really rare to find an institution where this is possible. In addition, some influential people, as I would call them, Professor Raats, a very well-known soil physicist who really shaped me in the beginning of my career and taught me that we really need to understand and build mechanistic models. And they will help us to put that all together, that system. And then I went to Cambridge. And I still remember when I was going for interview there and the question that I was asked, how many parameters has your model? And I thought, is that the most intelligent question you can ask? So I started counting. And then he interrupted me and he said, we need to have some discussion on this. And I couldn't figure it out. But really, there I was more introduced to the systems approach. So we look at how systems behave and try to understand the behavior of systems. It was epidemiological systems, so that shaped the basis of a systems approach in epidemiology. But I've learned from that, and I'm now beginning to see and think about how we can bring that understanding into soils. Within Abertay, Professor Hyphae and Professor Paul Freeman have been very influential in helping me to develop and shape and get my career going in Abertay, and my family. I would like to thank them for the support that they've always given to me, and also for sharing the time, because they haven't seen an awful lot of me lately. The Scottish Informatics, Mathematics, Biology and Statistics group, many of them are here in the audience. Really, they're most of the people that do the work. And it's been very pleasant to interact with them. And I think it's absolutely crucial that we've got all those skills together in one area where we can together face those challenges that we cannot face on our own. So this is the last slide. And I'm sure when you all came in, Most of you will have focused on the last bit of the title, that only a thin layer stands between extinction and humanity. But I hope when you leave this room that you'll remember the first bit of the title, Soil Research Matters. And I thank you for your attention.
Thank you, Professor Otten, for this fascinating lecture. You've given us an interesting insight into the complexity of a massive but often invisible world. A world, the dynamics of which will ultimately govern our very own existence. The case for gaining a better understanding of this resource is evident and strong. Only then can we hope to predict and manage what may ultimately determine our future. I know that your passion, your wisdom, and your drive will contribute to this research agenda, and that you will help guide the development of research and researchers in the wider Abertay community. Professor Otten, I would like to convey my own and the audience's thanks for this.